Um, yes, the tips and tricks for GraphML. Hello, everyone. As Murat introduced me, my name is Ebru, and I work as graph consultant at OpenCredo. This is a graph model, and sometimes I will have this on the right-hand side. I will have the model, whereas on the left-hand side there will be data represented. I will talk about why and what of graphs, why we need them or how they are useful, how to model a graph. It is a bit different than relational databases and how we look at that space, how to apply the model, which we will talk about the fraud detection use case. So our topic and data set will include some accounts and some frauds. How to select the tools. There are a couple of tools available on the market. Some of them are good for different reasons, so we will go through them. And also, how do we run the algorithm? So this is a basic graph, more of graph algorithms in terms of the analytics, but we will walk through the code as well. So why graphs? I'm opinionated. My answer is simply it's intuitive and you can represent it very easily, as I have shown. This is, for example, a talk that is given by a speaker. On the right-hand side, my model, and the guest attends and rates. You may suggest this is also doable on the relational databases that we can save talk, speaker, and guest as tables. What we can't do is being able to represent the relations as the first-class citizens. So guests having attended and rates between talks is a luxury to have. Also on the left-hand side, we can see so many nodes. So each data itself is first-class citizen. We can hop from one node to the other by using the relationships, and we can traverse the graph as many as we want until we reach our data. We filter the relationships that we go through. If you don't believe me, this is CEO of NVIDIA, Jensen Huang. In November 2021, they had the GDC annual conference, and graphs are the native format, the most natural data structure of the world's data, is his words. He showed one of the drug discovery, 4 billion molecules for the chemical database interactions and how they form. On the right-hand side, this is the social connections and fraud detection. By Amazon, it's 90 billion relationships on a social network. On another one, AWS, actually, this was last week, Mars 2022, Swami Sivasubramanian, apologies for pronunciation. He's the VP of Database and Analytics and ML at AWS, and he suggests graph neural networks are the next big thing. Just as a disclaimer, today I'm not going to talk about graph neural networks, maybe a good topic for the next one, but today I will talk about the fundamentals about the graph, how we model it, how the graph analytics works, and the basic graph algorithms. So, but going to graph neural networks, first we have to understand the graphs. So we are doing the first step. What are the implementations that we see for the graph models? One is Hyperfoods by Imperial College London. They pick the existing drug, the formation, the structure of them, the protein interactions and the food, and with the molecules, with the interactions between them, they managed to find the cancer-beating molecules called hyperfoods. And they just modeled the graph by network effects of the interactions. Another one is the recommendation engine by Pinterest, just not by using the picture as an object detection, but also the semantics of it with the annotations and other properties of it. They managed to understand the graph, the picture better, and be able to recommend the users and their interactions between the pictures and or the pins, as in the pin board that you usually use, and the users, how the interactions are there, and they can recommend better pins for the users. Another one is Airbnb, that they had the onboarding. So when they have a new host, they wouldn't know how to onboard if they haven't updated their profile. If they have minimum information, they wouldn't know what to do. So what they have done is be able to use the first level and second level hops on the hosts to find the relationships. If they have shared in the locations or the photos between those hosts, they can find what they can for the next onboarding process, make it easier without any historical data or observations. So they have a baseline of the understanding of the knowledge, that's more factual information about the user, the new host. Another one is Google Maps. From point to A, it's a map that anytime you check out Google Maps, for the ETA, the estimate time of arrival, they can calculate the node passage, the message passing between the nodes and understand where the congestion is going to happen and recalculate the total estimate of the time from A to B. By DeepMind, it was implemented. What is a graph? In simple terms, graph is made of nodes and edges. If you are already familiar, apologies, just one slide. If only one type of the node exists, it's called homogeneous. If there are multiple nodes, it's called heterogeneous. Apologies. If there are only two types of the nodes, as the user and the product, the pin stage recommendation engine is the example. It's called bipartite. So we can create a distinct set of node A, node type A, and node type B, which make the interaction kind of the graph bipartite. Otherwise, it's a simple graph. Between the edges also, we can have weighted, which means the weight between two nodes is different and can be different for each node. In the Google Maps example, it could be distance, it could be weight, it could be time. Different types of settings can be done, but the relationship has an extra property that we can evaluate. Unweighted graph behaves, all the nodes are equal, usually count as one, so we don't have to calculate. Also, the edge can be directed. So from and source as a source and a target can be important, then we call it as a directed graph, which is a standard kind of example is how we do the follow for the Twitter. One person follows the other, the directed one. If you don't care about the relationship's direction, then it's called undirected. So what does graph machine learning pipeline looks like? Usually we have nodes, we have data, we have extracted from all around the world with APIs, external data sets, SaaS products that you may have, internal on-prem data sets you have been storing. It could be structured and unstructured data. With the structured data, you ingest and populate your graph. With unstructured data, you may want to run some knowledge graph extractions for the entity recognition or link recognition, which makes your data enrich. And then we can run predictive analysis. This is more of calculating the size of the graph. It could be, is it a connected graph? Does it have clusters? Does it have a hop, which is usually a big chunk of cluster that we may want to just focus on that, or we may want to exclude that from our graph. Then we have actually subgraph because we filtered, we run our feature engineering in a sense from the graph. Then we run either supervised or unsupervised machine learning algorithms on that subgraph. Thinking we have usually millions of data, millions of nodes we are working with, it's very important to run the predictives and to have that subset. And then we can train and test the machine learning model. We publish it, tune it if the accuracy is not what we wanted. It's just a standard machine learning loop that we have to iterate through. It is important for each graph that we have the adjacency list and the metrics. This is the Karate Club, a study of members of the club. Each node represents a member, and the relationship between them is one, which is actually in the metrics, we can see if there's a relationship, it's counted as one. If there is none, it's represented as 0. Why it's important, this is how we store the relationships. The adjacency list is mostly used. And this is unweighted, undirected graph. If we had weight, possibly adjacency list would have another column to represent that weight. And also the numbers here, the adjacency metrics would have 2, 3, depending on X, the number X, whatever the weight is. So it will look different, but looking at the adjacency metrics and list, we can understand what the graph is and what we can do. So how do we model the database? We said we are going to use the fraud detection algorithm. So this is a basic example of an account node. An account may have a phone, a social security number, and an email address. These are usually in the table, in the relational database, stored as one table and one properties. By extracting this information as the phone having its own node, we can find out other relationships with this node data itself. And in the case of, if we wanted to have address, for example, we may want to use other one encoding or GPS recording location, XY, latitude and longitude information as type of feature engineering processes we have done. But in my simple scenario, we don't need any, we will just use the phone, email, and SSN. For the data set, I will be using Neo4j. Neo4j is one of the proprietary databases, graph databases. They offer a free sandbox environment where you can run the built-in data sets. They have for 3 days, can be extendable to 7 days, and it runs on GCP. So what does it look like? The top is Cypher, which is one of the languages, graph query languages that is used by Neo4j. I do match the account and return either the phone SSN or the email address that the user may have with any other node. In the simple kind of form, I have all my nodes. They have an email address and SSN and the phone number. This is just the data set. It looks without any change or modification has been done. If we want to zoom in and look at one data set in that big graph, this is the user. The account has email address with that relationship, SSN, an extra node, and has phone, which is also a node on its own. So what we are trying to find, what's our goal? In our use case, Alex may be a node, a user, but we don't know if it's fraudulent or not. He may have some email addresses, phone numbers, SSN numbers. These could be shared with other users, and we don't know if it's the address or the email address. Is this fraudulent or not? Was this one person trying to have multiple accounts just because they need 2 accounts for random reasons, or was it a fraudulent, a real intention that they want to hack the system? So by creating or by finding those fraud rings, that we can able to understand how connected this is actually a component, how connected the nodes are, and we can figure out if this is a fraudulent user or not. Igor, in this example, maybe we know it. This is part of the testing and the training data set for some training data sets, we maybe already know about Igor, or we know it, we just want to find out the links and the hops, how many hops they can go through and how many users have been impacted by that fraudulent actions. There are many algorithms that we can run. Each one has its own use case. In the example, to start from the last one, in graph fraud use case, we are talking about the communities. So it's more of understanding how they are connected. But also it could be the influential kind of, in terms of the other algorithms, we may want to find out who is most influential. This is one of the common examples that's known, actually. One is PageRank algorithm by Google, made Google, which calculates the ranking of the web pages and finds which is the most relevant, which is still in use if there are same relevancy scores. They do sort by PageRank algorithm. The second is how events are connected from one node to the other. How do we travel? And Google Maps is a good example of this one. It's a path-finding algorithm. So you can find out from the nodes, how does it take, how long does it take to arrive from A to C. There can be also isomorphism in terms of the similarity detections, how the two graphs are similar. It could be not just the isomorphism of the graph, but also it could be how the nodes are similar, how the edges are similar. And the last one is how the graphs are similar. It could be finding anomaly detection, the unusual activities with their rankings within the graph, or it could be infer the semantics, where you create the knowledge graphs with the ontologies and try to understand the relationships. And when you have a text or a data like wiki, you can understand the big pictures and ask questions to be able to get answers. This is how also Google search is working behind the scenes. It has a knowledge graph. But what we want to focus on today is the communities. So to understand how the clusters form and how we can verify there's a fraud ring or there's a community of people doing bad things. Back to my example, I have a client. It has an email or phone address and is any node. The flexibility of being able to represent email, phone, SSN as separate nodes, I can just abstract the node itself and find out who else, which other client is also sharing the same node. And I can get the count of it. So from this ID, a random user ID, to another ID, there were two relationships, which means they shared either email address, phone, or SSN, two of those three properties. Then we can get the count very easily. Why we want to look at the connected components? It's good for pre-processing to understand the big picture of the graph, to be able to create the components that we want to focus on. Usually it's run as the pre-processing step for most of graph algorithms. It does give us the disconnected groups, and it's good for the recommendation engines and kind of to find out what we can offer, understand the subset of that graph. So what it does, basically, in simple terms, pseudocode, for each node in the graph, we will just collect the visited nodes as the breadth first search. So it first goes to all the parent-child relationship. It first goes through all the childs, collect them, and tries to find how far it can go. Once they are visited, it adds to the visited nodes. And also because this is now a node's component, it will loop through and add to that component until it finishes all the graph. It's the MP complete, so it has to travel all the graph and find out all the components of the graph. So how do we apply the graph? Now we have a data, we have the subset, I created this subgraph WCC for the weakly connected components, which makes it easier to focus on. Because as I said, we have millions of nodes. We are not going to be able to run all the data. And it's an MP hard problem that we may not be able to have time, resources, or we just want to focus on a specific use case. It's great to have a projection of the subgraph. And for the account label, we will create a shared identifier. So what we do is create a virtual relationship, a new relationship between those two nodes, identified, called shared identifiers. And we will put account for the properties, which will say that between node A, account A, and the node B, account B, there is X number of shared properties, shared identifiers. So for the next phase of the query or the algorithm, it will be easier for us to focus on. This is after the shared identifier. It's similar query, but in terms of the shared identities now, we managed to get the result by the node accounts and how the components actually formed, because we have the nodes sharing the same identities without running any graph algorithms yet, just running the basic shared identifier of the query we have run. We can understand which nodes are connected and what are the subcomponents of that big graph. It's a very quick win in terms of the first step exploration. For the second step, now what we want to do is we want to assign some IDs, because each component is somewhere abstract. We can't identify which has the fraud ring 1 or fraud ring 2. So we assign like a component ID. We assign an ID for each number to each group. This will be the fraud group that we will say, and it will be the cluster ID. For that, it's iterative consecutive ID, so it will give a consecutive ID for each fraud ring. We pick the size of 1 bigger than 1. It's the kind of to make sure that we only consider bigger ones. If your use case is different, this can be changed depending on what you are looking for. So if we want to look at those now fraud rings, we collect all the fraud groups from the group IDs, and we can find the rings now. It's more explicit and valuable to be able to identify each node has a property. Whenever we query next time, we can see what the fraud ring ID it belongs to, so we can easily write the queries, getting the node attributes as a new property, and run into the machine learning algorithms. So what does it mean in terms of the nodes and edges? Now I have a node file, or I extract the information from the graph database, which looks like more of the account ID, account name, and the fraud ring ID, which we want to focus on. We can identify 0 means it doesn't belong to anything, so it's just a random kind of ID, but I started from 1, and the source and target is the relationship. These are the IDs of the accounts from and to, and how many shared relationships they had. So what do? I have kind of managed to extract. I'm here. My next step is to run a graph machine algorithm with a tool. Which tools are there? This is one of the GraphML's actually representation of the evaluation. It's a nice and covers most of the steps, so I included here. GraphML is a new one relatively to for the other ones. How it implements graph theory. We should be able to traverse the graph, the first one. It means that we can run hops multiple hops from one to the other and be able to find out how many paths can we go through. Network stats is important in terms of the graph space to understand what's the local coefficient, what are the steps, and how we can get the how many components are there, how many, what size of it, how dense is my graph. And communities is another one. How do we understand how many communities are there, how we detect them is another one for understanding graph. Statistical models, we should be able to run embeddings, or we can run the model fitting, run simulations or hypothetical testing. Not all of them supports it, and plotting is the visualization. pip install is the external one. My favorite is the Network X. I've been using for a long time. It does support all the graph theory. To a level degree, it does embedding, which I will show in a second. It can run the what-if analysis for the simulations, and also it can do the basic plotting, which is the visualizations. Yellow checkmark partly supported, not all of them, Anthony. For the, so if we go to the training and testing the data, we have the nodes account CSV. It's how we ingested kind of the first picture I have shown for the account data. We may add more attributes depending on the case. I have just included the names, but we could have added more edges or nodes. And the edges account, I have just included the source target and the score of the weight, how many count of relationships they had. We will load the graph. This is the NX, the Network X library will give me the G graph. And we will run the embeddings, and the output will be on an embedding. What we could have done is here to take a sample size and run the embeddings, because it's going to be huge, big, possibly. Depending on your use case, you may not want to run embedding on the whole graph if we are talking about millions of nodes. Then we will split the data with those embeddings, depending on kind of what we had. And then we will run the train the classifier and test the classifier with the accuracy score, whatever it's going to look like. The first one is straightforward, so I don't have the first one. Loading is just you add new nodes, you create from edges, and either you create from edges or you add extra edges and nodes as part of the graph attributes addition. For calculating embeddings, I use the Volcker one. This is, it has a node to make random walks. So you define how many walks it's going to do, how many nodes it's going to start, how many lengths. It has P and Q is the biased walk, which means you have an opinionated walk from outward versus inward walks. Not to make random walk is usually, takes the walks, and we will define the string, or it's the array of the walks, and then we will apply the word2vec, which gives me a vector size of 128. It's a bit big. We could have actually done a bit smaller, and we will save the embedding in a file. And we can split the data. Splitting is quite tricky. It's very tricky topic in terms of the graph data science. Where do you split the data? Do you want to split your data in terms of the nodes, in terms of the relationships, in terms of kind of, you may have extra labels for your nodes. An account may have extra labels depending on it. I didn't include, kind of, I had just names, but it could be nationality, it could be have other things that you may want to location-wise. And then split that graph. I just used the fraud ring ID because that's what we have and what we are going to possibly predict in the scenario. Just 8 to 20, so the size will be the 20% of the data set. And then we will train the classifier. I used the logistic regression. It could have been another one for the cross-validation. And then we will fit the train, and then we will test, run the test set for the classifier, and then we will run the accuracy classification score for the prediction. And then if it's not good enough, of course, we have to go back to our parameters, how we did the embeddings, how we did split, and before step, how we apply those ones and get a better result. There are some nice recommendations for the books. That's the kind of basic of my talk, actually. Connecting the dots, harnessing the power of graph is my ebook that I'll put onto the chat as well. It's a free ebook. It's very business-based, actually. Book just to go over the use cases, to talk about all the graph algorithms for the PageRank. For the PageRank algorithms, kind of any kind of community detection or any kind of algorithms. A handbook of graphs and networks in people analytics is actually a good book in terms of the R and Python examples to explain what types of analytics can we do in the networks. And graph machine learning is, they have some data sets for the graph machine learning algorithms in terms of the public data sets that they have run algorithms. That's it for me. Any questions?
There are questions in the chat. Will you see the chat?
Yes, just a sec. I need to open the door. Apologies for this real long.
It's okay.
Hi, apologies. The embedding part is based on what criteria? Can the speakers, can the attendees talk, Murat, or are they?
You can let them talk if they raise their hand, I believe. Says I can talk, but you cannot hear. That's a good one.
I see. I think Bo is not here anymore. From the, oh no, I can't see. It's at the top, that's why. Hi, Bo.
Hi. Hi, I'm just curious. So how you conduct the embedding in the code part you just showed us? It's based on what?
I have used Notevec, and kind of I first created a path, kind of what type of paths it can go, and then I applied Vertevec because I have strings of walks.
Okay.
Array of walks, and then applied it back.
All right. Thank you. Thank you.
Can you explain a bit more? Kind of, it can be done in different ways, so I'm open to any suggestions or different opinions.
So is this data time series, or is kind of like the a basic network, like the people connect to people?
Yes, it's just accounts. In the end, when I had the first level in the Neo4j in the graph exploration stage, I had the nodes, email addresses, SSN, SNN.
Oh, okay.
Different
So
nodes.
so it's not.
I had the Excel sheet kind of, which I showed. Then I have just accounts. So
Oh,
sourcing part
okay.
of everything
see.
became just node. So I had one.
Yeah, this is kind of the not the time series. Okay, got you. Thank you.
It's not time series. It's one kind of homogeneous graph with just one source, one account is connected to other,
Yeah,
and it may have a weight kind of on the.
yeah, I see. Thank you.
Okay.
Few more questions in the chat.
How will you model fraud detection in money transfer between accounts? GL. It is actually, this is the next step for the money transfer, because it becomes more complicated, where you have the in and out from the debited accounts and how they are transferred, which banks they are using. It does have multi-hops, and it's a great use case as well. But yeah, I haven't included in this one because I wanted to make it simple. The data set I'm using is actually has all the data sets available for that. So just adding more nodes to the graph and being able to find those communities, the clusters of fraud rings, using a kind of more complicated queries rather than using has SSN, has email, has phone, the query I had for the relationship type. I had to extend to the in and out, the payments and the transfers, all kinds of relationships they have been involved with. If that's not a good answer, please, GL, raise your hand so we can allow you to talk. Thank you, Roger, for listening. Use of GCN and graph models in image and video processing. GCN is not one-to-one mapping to image and video processing. It's actually being able to use GCN. This is not typical of, as I said, graph neural networks should have its own presentation meetup. But for just a simple topic, image use usually is an X dimensional, a square matrix you have similarly to the video processing. So you apply, actually you present that as the adjacency matrix, and then take that into the GCN. What the graph neural networks or the graph models enables you is, and my use case unfortunately was the simple between the nodes have the same number of properties, you can have an adjacency matrix, but being able to has unknown number of relationships and unknown number of connections from one node to the other for different nodes. It does have different use cases rather than just image and video processing. So it's not one to kind of applicable to the GCN specific. I can share the presentation, of course. I'd like to know if new categories of data can be added onto Go for applications like knowledge discovery. Yes, updating graph is costly. Creating a new graph usually is easier, but you can always add new nodes. It's extensible, kind of any graph model we had here. We can always, for the simple use case, if I want to extract, for example, as I said, if we had address, we could use the different properties, but let's give an example of what we had for the email address. I can just split it, this node with maybe the domain names. I can create another node with the relationship of that user, the account, which email domain or it's using. So it's very easy to be able to extract with matching those nodes and creating the relationships and nodes. It's very extensible in a sense, and it's very important to know what you need, because otherwise you will have lots of data that the graph will get bigger and bigger. And this is the most common problems in the graph space. We have to be able to identify what we need. But it's very easy for the knowledge discovery, and it's very easy to extend either by adding a new relationship or adding a new node. It is not recommended to update the graph itself. The concept embeddings is the same as clustering. It is not. Embedding just creates a representation of the nodes, but also actually you are right. It represents how close they are. It depends which clustering algorithm you are using, which embedding you are using. There are different type of clustering community detections. For example, why it's not exactly the same. You could have used similarity, which I haven't discussed. You may have node level similarities, relationship level similarities, and graph level similarities. And if I take the embeddings, it would be more close to it, because then you have a numerical distance between two nodes to represent the similarity. And that is more intuitively similar and close to the embeddings rather than clustering. So I wouldn't put the clustering and embeddings as the same thing. Usage for predicting loan defaulter. I'm not quite sure what does it mean. I'm afraid you may have some hands. Yeah, Shubham, if you can explain that. I'm not quite sure. I don't understand what the loan defaulter means. Source and destination accounts addresses come into consideration. This is how do I see the participants? Yes. Gian, I think this is your question.
Oh, I just want to understand that the output from the node to VAC is it like a sequence of node like ID, and those nodes, are they only accounts node which we traversed, or it includes both the accounts node as well as the attribute node which connect different accounts? And I understand that later you use the word to VAC to kind of convert them, convert this sequence into a vector. But I just want to understand the input. Are they, you know, just the randomly traversed accounts node, or randomly traversed accounts and attribute node? Thanks.
Thank you, John. In this example, it was just accounts. I tried to make it simple. It didn't use any properties in this scenario.
Okay, got you. And therefore, the embedding, output embedding of out of the word to VAC is a summary of the subgraph of a particular input, like the summary of the subgraph, right? Like being traversed.
Mm-hmm.
Okay.
You can select as I could have filtered, and that's why I had the suggestion to run the embedding for a subgraph rather than the whole graph, because it takes much time and the output is so big as well to be able to compute. You may pick a source, you may pick or set of rather than being randomly selected, you could have a subset of the graph and then assign kind of those nodes and find out the embeddings of those nodes.
Mm-hmm. Yeah. Okay.
I think it could have been better. It's because my data set was already small. I didn't want to make it smaller than I wouldn't be able to get any output. But if we are talking about million node of graph, then yes, I should have 1,000 or 10,000 subsets of the nodes I should focus on first, and then start the bulks from those nodes.
Yes, because ultimately, I think the goal is to detect fraudulent subgraphs, right? Like fraudulent clusters of nodes. I guess like the embedding is the scope of the embedding is typically constrained to a cluster of nodes that are more likely a representation of fraudulent connectivity, isn't it?
Yes, exactly. Otherwise, I'm going to miss the fraudulent ones. You are very right, actually. I was trying to get the example simple. That's why I cut lots of corners. Apologies for that, but your point is very correct.
Yeah. Okay. Thank you.
Thank you. And Salak, I don't know if you pronounce your name.
Hi.
Hi.
Yes, it's Zalak.
Hi,
Uh, Hi. Actually, I wanted to know that can we use this graph theory for the named entity problem?
Yes, definitely. Um, yes, for NLP, named entity recognition, it's actually how Google creates this knowledge base, and when you run a basic search, it runs through the annotations, and it can it can use word2vec and other algorithms. It has special algorithms on NLP side, and starting from the ontologies, because ontology is a graph to start with, being
Okay.
able to create the knowledge graph and then understanding all the documents referencing and how they are linked back is a very common graph problem.
Oh, okay. So like for the eBay products, if we want to find out that which one is the brand in that or which one is the product or something like that, we can do using this graph.
Yes, actually eBay is using, I don't know if that was you have read before, or eBay is already using the knowledge graph to be able to show that. If I go to I can't remember the link now, but sorry if I stop here. And it's more of the recommendations for the eBay use case, as far as I remember, but they do. I couldn't find the link. I'll share on the YouTube when this is posted. I'll share the links now. But yeah, there is also a good book on by Alessandro, which sorry about that. Yeah, I'll share in a minute.
Yes, that is okay. Like
Ravi asked about it. Sorry. Did analytics and data prep in Neo4j? Yes, I did. What other tools used for? Are they maintained open source? Apache Jena is one of them, kind of it's the common one. Janus, sorry. Janus graph. is the open source one that you can use. It's there's also ArangoDB, Tiger Graph, and other available databases. This was the free community edition of Neo4j, and the kind of Neo4j started with open source. By the way, it has community edition, so you don't have to pay money, and you can use for internal pre-production use cases. Man, you don't want to scale if you don't have to deal with billions of data, and you don't need the clusters of nodes that for the read and write replicas. Have you tried GraphFrames? I haven't. It's on my list, Ravi. It's on my list, definitely. I think that's it. I can't see any other question. Yeah.
Great. It was a great presentation. Appreciate your time. And people actually can also watch it in YouTube later. Thanks for everyone participation. You've been same number of people been listening for a while. Thank you.
Thank you.